All right, so now we can look at some explicit examples of these rank 1 Lie groups of Iwasawa type. And the first example I want to discuss are the real hyperbolic spaces, RHM plus 1, which I think are fairly well known. I guess everybody should have seen it at some point. So these ones can be viewed as, well, as R plus semi-direct product with Rn, where then the Lie algebra is a one-dimensional Lie algebra in semi-direct product with the n-dimensional abelian algebra, right? And commutators here are supposed to satisfy this relation. So for some fixed element A of the subspace A. So essentially what this tells you is that the adjoint representation of A restricted to Rn should just be the identity map. So the nilpotent part of the Lie group of Iwasawa type uh, is then, or the Lie algebra of Iwasawa type is Rn here. So this is just abelian. So in particular, also nilpotent. And as I already mentioned, the adjoint representation of A is the identity map when restricted to n. So in this case, we only have one eigenspace. So m is equal to 1, and the eigenvalue lambda 1 is equal to 1 as well. And in this case, if you plug everything into the previous into the formula from the previous slide for the Laplace-Beltrami operator, you get the following. And well, this is the well-known formula for the Laplace-Beltrami operator on the real hyperbolic space, which just sort of confirms that that everything is fine, at least so far. And then the second example I want to discuss is slightly more complex. And this is the case of the complex hyperbolic plane, CH2. And this, I don't know how well known this one is, but well, either way, I think it's a good a prototypical example, let's say. And this one can be viewed as R plus in semi-direct product with H3, where H3 is the classical three-dimensional Heisenberg group. And in this case, we see that the Lie algebra splits into the usual, as usual, into the one-dimensional abelian subspace, or I mean, of course, it's abelian since it's one-dimensional. And then we also have the Heisenberg algebra, which is the nilpotent part. And then we have four basis elements. Well, we have the basis element A, which spans this one-dimensional part A, and then we have X, Y, and Z. These guys span the Heisenberg algebra H3, and you can see that from this last commutator relation. This is basically the usual commutator relation for the Heisenberg algebra. And then these other three commutator relations basically tell you that X, Y, and Z are supposed to be eigenvectors of the adjoint representation of this fixed element A, and you want them to have eigenvalues 1/2 and 1 respectively. So basically, the adjoint representation has two distinct eigenvalues, 1/2 and 1, and the nilpotent part then can be decomposed into two eigenspaces, n1 and n2, where n1 is spanned by x, y, and z, by x and y, and then n2 is spanned by z. And so the notation is here slightly different than what we had before. So basically here x would correspond to x upper 1 lower 1, and y would correspond to x upper 1 lower 2, and then z would correspond to x upper 2 lower 1, right? And then if we also denote the coordinates analogously in some sense, then we can, using the formula from the previous slides, we can obtain a formula for the Laplace-Beltrami operator, right? And this is what one gets if one plugs everything in. So you see here that I mean, things get more complicated than in the case of real hyperbolic spaces, but at least for this particular example, it's not too bad. It's still sort of a presentable formula. Okay. And then, well, I will not discuss any more details, any more examples in detail, but I'll just mention a few more because I mean these rank 1 Lie groups of Iwasawa type really include a lot of spaces. So, for example, they include the Damick-Ricci spaces, which, well, they are also a sort of a generalization of these hyperbolic spaces that I presented, but also the quaternionic hyperbolic spaces and also the octonian plane. So these Damick-Ricci spaces are already a wide class of spaces, and then these Lie groups of Iwasawa type are an even bigger beast. Then you also have the homogeneous spaces of negative curvature where you need to assume additionally that adjoint mapping of A, adjoint representation of A restricted to N is symmetric. And then if you assume that, then the other two properties you needed for Lie group to be of Iwasawa type are automatically satisfied. And in particular, you automatically get rank 1 as well. And then the third example is that of Einstein solved manifolds. And here you actually need to, well, here you would actually need to assume that it has rank 1 for this all to work. But other than that, if you have any Einstein solved manifolds, you're good to go. It's you can present it as a rank 1 Lie group of Iwasawa type. All right. And now we can start discussing the heart of the talk and the heart of the paper, which is the construction of p-harmonic functions on these spaces. And I want to start by giving you just the idea of it all. And so, firstly, one can easily show that if one takes a harmonic function h, which is independent of t, so which only depends on the x variables, and one defines these two functions, where I again recall that n is supposed to be the weighted dimension here, which depends also on the eigenvalues, then these two functions are proper p-harmonic. And this was in some sense already expected and already known, because the functions of this proper p-harmonic functions of this form have been obtained for some other spaces. So for example, for the real hyperbolic spaces, this was already known. So it was kind of expected that this should hold in the general case. So for any rank 1 Lie group of Iwasawa type. However, this condition of H being harmonic and independent of T is often quite restrictive. So in some cases, you just get you just get functions that are, for example, affine in X and things like that. And so it's often not very interesting. And well, it's a natural question to ask, well, what happens if I don't take a harmonic function? What happens if I take an arbitrary function H, which is independent of T? Can I somehow modify this phi p and psi p to obtain a proper p-harmonic function? So that's essentially what we want to do. We want to relax this condition. And then, the idea how to approach this is, well, we want to add some correction terms, basically, to phi p and psi p to cancel out all the things that become added once you start applying the Laplacian, because H is not harmonic in this case. Okay, but to do that, as you can expect, we need to really understand the structure of the Laplace-Beltrami operator when applied to a function which is independent of t, so which only depends on x. But if we look at the formula again, so as I already mentioned, the biggest problem is that if you start with a function that doesn't depend on t, then once you apply the Laplace-Beltrami operator to it, you get something that does depend on t. So you in particular get this t to the power of 2 lambda i's here. But the good thing about this, so it's not also bad, but there is a good thing about this. Well, at least you can see how it depends on t. So there is structure here, right? So you have an explicit structure here on how it depends on t. So what I mean by this is that if you take a function which is independent of t and you apply tau to it, then you get some sort of a sum. If you think here, if you just isolate the sum with respect to I, then you get this t part, t to the power of 2 lambda I, and then all of the other sum and everything that remains is something that depends only on x, right? So you get some sort of a function hi that depends only on x in each term of the sum. So this is the general structure of the Laplace-Beltrami operator when you apply it to a function that depends only on t. Just for the sake of explanation, let's call H the parent and then Hi its children, right? Then because we want to sort of apply the Laplace-Beltrami operator several times, then it might sound natural that we would want to also find out what the children of these guys are. So for each Hi, what are their children, right? So each of these Hi's is going to also have m children, right? And each of those children is going to have m children. And as you can imagine, this gives you some sort of a structure of a tree. And this leads us, well, this leads us to a new concept called tangent trees. So if we're on a rank one Lie group of Iwasawa type, and we take a function h which is independent of t, then we define its tangent tree to be the collection, the following collection, where, so just let me first explain the indexing here. So this I here, the upper index, tells you which level of the tree you're on. So if I is equal to 0, that means that you are basically just looking at your original function h. And then if I is equal to 1, you're looking at the children of h. And then if the I is equal to 2, then you're looking at the children of the children, right? And so forth and so forth. And then this lower part alpha, this is a multi-index. So here we define some sort of a multi-index set, which you don't have to really worry about it now. I'll present an example on the next slide, so it'll be easier to understand. But this basically tells you sort of the path to the children. It tells you how to reach that exact child, this particular child, you know, in the tree. So it tells you where it needs to be located in some sense. And then, well, how do we generate it? As I showed on the previous slide, basically we take the Laplace-Beltrami operator, and then we extract this sort of these coefficients in some sense, because this can be viewed as a polynomial, in the t variables, and then the coefficients depend on x, and we extract these coefficients, and then these are called the children. And then we first do this for h, and then we iterate it for each of the children. We do the same thing basically. Okay, but then we also, there's another concept that's interesting here, and that's called the degree of the tree. And basically we want to know, does the tree terminate at some point? Does it at any point happen that none of the children have any more children? So in some sense, we want to find if there's a smallest I such that the next level of the tree is empty, in some sense, that everything the next level is 0, then this I will be called the degree of the tangent tree. And of course, it could happen that no such I exists. It could happen that all the children keep breeding, and you have infinitely many children, right? And then the degree is said to be infinite. But as I promised, I think this is best it's best to look at an example to understand this. And so if we go back to our complex hyperbolic plane, which was sort of our non-trivial prototypical example, so here I wrote down the Laplace-Beltrami operator of a general function which is independent of t again, and I rearranged the terms a little bit so it might not look the same as it looked on the as it looked on the slide before, but I arranged it here so it's easier to follow what's going on with tangent trees. And okay, now for example, let's take the function h equal to z to the power of 4. So this is a function that's independent of t, so we should be able to generate it its tangent tree according to the previous definition. And so what we do essentially is if we plug in z to the power of 4 into this formula for tau, then we get t times something. Well, here, because our function only depends on z, then if you look at all the terms, you see that only the middle term will be non-zero. And if you calculate it, you see that this is equal to, well, the second derivative with respect to z of this is 12 times z squared. So this thing will be 3 times x squared plus y squared times z squared. And that's your first child then. So the first child is then the coefficient next to the first power of t in some sense. And then the second child is the coefficient next to the second part of the next to the second power of t. So here we take just the second derivative with respect to z. So this will be 12z squared. And now we iterate this. So for this child, we calculate its children. So again, we just plug in this function into here, and then we take the first coefficient, that's the first child, and then we take the second coefficient, that's the second child. So yeah, and here you see, so this multi-indexing, here you see how it works. So basically this, like this 1, 2, 1 here means that you should first take the first child, so the first power, and then the second child, so the second power, and then the first child again, because this is the coefficient next to the first power, right? And then here there's no second child because it's equal to 0, right? Because here, if you look at this function, this coefficient is only a derivative with respect to z. So here the child h3 1 2 2 is equal to 0, so I just omitted it. But that's basically how the multi-indexing works. It basically just tells you which path you need to follow. All right. And now we can finally state the main result, this sort of general construction. So what we do is we take a function independent of t, and we take its tangent 3, and we suppose that it has a finite degree, which we so finite degree r. And then I have to introduce some more notation now. I'm sorry, I know that there's a lot of notation, but that's kind of the nature of it. So basically, we define this lambda k alpha, these big lambda k alphas, and basically what they tell you is, if you look at this, so you remember that this alpha was the path to the child, and so what this means is that if you follow this this path up to the level k, you want to sum up all of the corresponding eigenvalues along this path. And this just appears in the formula, but I mean, again, it's not super important to understand this unless you want to look at the proof. But yeah, and then we can define our correctors, our correctors in the t variables in some sense. And well, this is quite a nasty formula here, but well, and of course we didn't yeah, but okay. So it's quite a nasty formula, but once you start looking at it, you see why each of the factors, each of the terms is necessary. But anyway, so once you define these functions which only depend on t, then you can finally sort of take your phi p, this usual phi p that we started with, and we can correct it by adding this some sort of sum which depends on the elements of the tangent tree, and also on these sort of particular correctors in t that we defined here. And this is then a proper p-harmonic on S. And I wanted to mention before, but so I just wanted to say that of course we didn't just come up with this out of the blue. I mean, it took us quite some time to get to this general formula. So we started with some specific cases. I think the first case that we started with was when h when h only has one child and that child has no more children. So essentially you have your tangent tree consists of only like one node. And then we extended it to like the case when you have one branch. So when the sort of each of the children has only one child, and at some point it terminates, and then eventually we reached this sort of general theorem. So right, and then you'll remember that I like in the beginning of this section I showed you that there's another function. So if you put t to the power of n here in the middle, then we also wanted to modify that one, and there is an analog theorem for that. So I'm just gonna switch slides now, and you're gonna see not many things are gonna change, but some things are gonna change very slightly. So I'm gonna switch now. Okay, so you see the only difference is that basically in the definition of these correctors, we have plus n here, and this became a plus. It used to be a minus before. And then you basically define everything in the same way. You still have this sort of first part, and then you have this corrector sum, and then you can show that this thing is proper p-harmonic on S. Okay. And I just also wanted to mention that I was a bit sloppy. So if I go back to the previous slide, to the first construction, so here I was a bit sloppy with the statement, because you'll notice here that you have this thing in the denominator, so 2 lambda k alpha minus n, and this could become problematic because this could become 0. I mean, one can construct examples where this becomes 0. So in some sense, this construction might fail to work in certain cases, but then if I go back to the next slide, everything is fine here. So this one works regardless. So even if the previous one fails, this one will work no matter what. Okay, and so what's the idea of the proof? Well, the proof is inductive, so it's by induction. So first, what one does is one checks that phi1 and psi1 are proper harmonic. So you'll remember from the previous slide that phi p was the first construction and psi p was the second construction. So phi1 and psi1 are proper harmonic, and phi2 and psi2 are proper biharmonic. And that's not too difficult to check by hand, because like these, you can get a very simple expression for these ones. And then what one does is, well, for the induction step, one shows this formula for the Laplace-Beltrami operator. of phi p and psi p. So you see that they depend in a nice way, in some sense, on the lower order phi p's and psi p's, and this basically immediately gives you that these functions are proper p-harmonic because, well, because of we already checked the base case. And well, I mean, when you just state it this way, it looks very simple, but of course, I mean, you saw how these objects are defined. So naturally, the calculations that you have to do to obtain these formula are quite they get quite nasty, and you have to do some summation tricks and all that. I mean, it's nothing too difficult, but you know, it's easy to make mistakes, and it's you have to keep track of a lot of things. And well, this ends up being quite a long calculation actually. Right, but then so well, so then the natural thing to ask is, does this work on any rank one Lie group of Iwasawa type really? Because here we sort of started with the assumption that we have a function independent of t which has a tangent tree of some finite degree. So the question is, do these functions with finite tangent trees exist in general? And the answer is, well, I mean, maybe somewhat surprisingly, but the answer is yes. And I mean, there's a lot of them. There's a whole lot of them. And we managed to actually show that if you take any polynomial in the x variables, then this thing has finite degree. The tangent tree of it has finite degree. And I mean, this then basically tells you that the constructions that we did are parameterized by polynomials at least. So for each polynomial, so you could take your favorite polynomial and you could use it to generate the proper p-harmonic function on your Lie group, which is very nice. And well, this kind of boils down to the fact, as I said before. So when I showed you the general formula for the Laplacian, I said that it's not too important to know. It's not too important to know how these polynomials are defined. It's just important to know that they are polynomials. And this is where this becomes important. So it becomes important that they're polynomials, and becomes important. So here's where, I mean, their structure kind of becomes a little bit important here when you actually want to do the proof of the fact that every polynomial has a tangent tree of finite degree. But yeah, so I will not go too deep into this, but you can imagine that sort of these guys being polynomials is sort of the crux of the proof. And this you also do by induction, and here you do induction on the number of variables, or on the number of eigenspaces, in some sense, that the polynomial depends on. So what ends up happening is that so let's say that you have a polynomial that depends on the variables from all the eigenspaces. Then eventually, the further down you go into the tangent tree, eventually you're going to lose dependence on the variables from the last eigenspace. And then, well, you can do induction based, and then you start doing your induction. I mean, then if you go even further, then you're gonna lose dependence on the variables from the second last eigenspace, and so forth until you eventually reach a point where you lose dependence from of the variables from the first eigenspace. And so it's some sort of like a reverse induction, let's say. Okay, and then, well, this is basically what I wanted to say. In some sense, these were the main results. But then there are, of course, further questions. So the first question one can ask is, well, so this works for functions which have finite tangent trees, but what happens if the tangent tree is infinite? Can we still get some sort of a result? Because if I go back to the result, so you see here, one could imagine, okay, well, what happens if I let R go to infinity? Does this sum still converge? Is it still well defined? Does it still define does this whole thing still define a proper p-harmonic function? So this could still work, but because because we managed to actually get so many examples already with these polynomials, well, we managed to get so many examples of tangent trees of finite degree, we decided that we wouldn't really look into this. But it's a natural thing to ask, of course. And then another thing to ask is whether all p-harmonic functions on a rank one Lie group of Iwasawa type are of one of these two forms that I showed you. And Well, I mean, I would say intuitively, I would say that the answer is probably no. But well, one can never be too sure, and especially if one is able to somehow extend this to infinite tangent trees, then there might be hope that really every function is of this form. But well, yeah, this is also something that I mean, it's something that could be looked at. It sounds interesting. And then finally, what about higher rank Lie groups of Iwasawa type? So in the beginning, I gave you a general definition of a Lie group of Iwasawa type, and you'll remember that the rank was the dimension of this subspace A. And throughout the rest of the talk, we focused only on the rank one case. But I mean, of course, one could have higher rank Lie groups of Iwasawa type, and so the question is, can we do something similar there? Well, here we actually gave it some thought. And well, the first problem is that it's not as easy to set up a nice coordinate system in this case when you have a higher rank. And well, it's questionable whether it's even possible to set up such a nice coordinate system as we did in the rank one case. But there's another even bigger problem, and that's that we don't really know any explicit examples of higher rank Lie groups of Iwasawa type. And here, what I mean, of course, one could just cook up an example. One could just like set up the eigenvalues and set up the Lie algebra and all that, and then well, just basically cook up a random example that has a higher rank. But that's not really interesting. We would really like to have at least some space which is already interesting for other people in some sense, which has already been studied in literature or in some papers or whatever. And we weren't able to find any. So we weren't really able to find any Lie group of Iwasawa type which has high rank, which is sort of given as an explicit example. And so, well, if any of you know any example, I would of course love to know about them. I love to hear about them. But so this is sort of what demotivated us from studying higher rank Lie groups of Iwasawa type. But maybe if we find out about some spaces that well that have higher rank, then it could be an interesting thing to look at. Okay, and yes, that's all I wanted to say. So thank you very much for listening. I hope you enjoyed it, and we'll discuss questions on well on the Q&A. Thank you.